Welcome back. Today we're going to talk about how to use probability to help us make decisions. And the first decision we're going to make here is between these two games, Game 1 and Game 2. Game 1, I list out the probability of winning and losing. So for Game 1, probability of winning is 0.25, which is 25%. The probability of losing is 0.75, 75%. Game 2, the probability of winning is 0.70, which is 70%. The probability of losing, 0.30, 30%. Right off the bat, Game 2, you have a higher probability of winning than Game 1. Both games cost $3 to play. Game 1, if you win $15. Game 2, if you win $4. So there's a trade-off here. Game 1, you have less probability of winning, but when you win $15. You win a lot more. Game 2, you have a higher probability of winning, but when you win, you don't win a lot. And the question is, which game would you play? Which game is better? And how would you decide? So one way to decide is to look at the expected value of each game. So let's talk about how to find expected value. So I need to first write down the profit of winning and losing for each game. So for Game 1, if you win $15, but you have to keep in mind that you paid $3 to play already, so you actually profit $15 minus the $3 that you paid. So you actually profit $12, 15 minus 3. If you lose, you get nothing, so you lost the $3 that you paid to play. So I'm going to write that as you're down 3, or you're negative 3. And let's do the same thing for Game 2. Game 2, if you win $4, but you paid $3 to play already, so your actual profit is 4 minus what you paid, so 4 minus 3, which is plus 1. If you lose the $3 that you paid, so if you lose, you're down 3, negative 3. And now let's calculate the expected value. So let's first start with Game 1. And the way you calculate expected value is probability times the profit plus probability times the profit. 0.25 times 12 plus 0.75 times negative 3. And let's see what this is. $0.75. And let's do the same thing for Game 2. Probability times profit plus probability times profit. So 0.70 times 1 plus 0.30 times negative 3. And I get negative 0.2. All right, so I haven't told you what these numbers mean, but right off the bat, which one do you think is better? The expected value of Game 1 is 0.75. The expected value of Game 2 is negative 0.2. You probably want the game that has a higher expected value. So Game 1, and it's true. So what expected value is telling you is, if you play Game 1 many times, so when I say many times, I mean many, many thousands of times. If you play Game 1 many thousands of times, right, sometimes you win, sometimes you lose, but in the long run, it averages out to you winning roughly 0.75 each time you play. Okay, so if you play Game 1 many, many times, many thousands of times, each time you're playing, you're winning about 75 cents each time you play. Game 2, on the other hand, if you play it many, many times, each time you're playing, you're losing negative 0.2. So you're losing 0.20, which is 20 cents. So each time you're playing Game 2, you're losing on average 20 cents each time. So Game 2, you definitely don't want to play. Game 1, you definitely do want to play, especially if you're playing these games many thousands of times. So where would you play these games in real life? So one example would be a casino, right? A casino basically has game two. So game two, you win more frequently, right? So you feel better, right? There's lots of bells and whistles and sounds and music, so that it makes you feel better that you're winning. So you're winning more frequently, but each time you're winning, you're actually not winning a lot. So that in the long run, if you play, the longer you play, on average, you're losing money each time you play, which is how the casino makes money. Where else would you play these types of games in real life? So at some point in your life, you probably have to buy insurance or deal with insurance. And that's exactly a game of this type. So here, a company wants to offer an insurance policy to owners of the new iPhone 12. Based on extensive research, the company is able to estimate the probabilities of the following events. Lost or stolen phone, 0.01, mechanical repair, 0.02, cracked screen, 0.55, none of the above, 0.42. So if you're super careful with your phone, you're probably in the none of the above category. Now, if the phone is lost or stolen, the company is going to pay you $1,000 to replace it. The company is going to pay you $400 for mechanical repairs and $100 to fix a cracked screen. And the company sells the policy for $40. If you buy this policy, what is your expected value? So an insurance policy is essentially a game of this type. You buy the insurance policy for $40, right? So that's the cost to play. If your phone is lost or stolen, the company is going to pay you $1,000. If your phone is broken and needs mechanical repair, the company's going to pay you $400. If you crack your screen, the company's going to pay you $100. If you're super careful and you never actually use your policy, you basically lost your $40. So this is a game of this type that we play very, very often in our daily lives. And we're not going to go through the details of calculating the expected value for this example, but I'll tell you that in real life, the expected value of most insurance policies, or actually probably every insurance policy, is going to be negative. Okay, that's the only way that the company is going to make money. Now, one thing I want to point out is that the expected value, these numbers, come into play if you're playing these games many thousands of times, right? If you're not going to play these games many thousands of times, then you would decide differently. So if you're only going to play the game once, would you pick game one or game two? So that's a different story. If you're going to play a game once, you might not want to play game one, right? Because game one, most of the time you're actually going to lose. And the only way you actually make profit in the long run is that you actually have to wait until you get that big win. And if you're only going to play once or twice, you might not make it to that big win, okay? Which is why you might not choose game one. Whereas game two, most of the time you actually win. You just don't win a lot, right? So if you're only going to play the game a few times, then you would make your decision differently. Expected value only comes into play when you're playing the game many thousands of times. So for insurance policies, right, you're not going to probably buy a phone many thousands of times over your life, right? So even though it's negative expected value, you still would probably want to buy, you still might want to buy an insurance policy. Now, from the company's perspective though, right, whoever's selling this insurance policy, they are playing the game thousands of times, right? Each time they sell this to a customer, they're playing the game. So for the insurance company, they're playing this game millions of times because they're selling this policy to millions of people. So for the company, the expected value is important to them. And same thing for a casino, right? If you go to the casino, you might not play a lot, but the casino is actually playing the game with many millions of people. So with everybody who plays the game, the casino is playing that game. So the casino is playing the game many thousands of times. So the expected value is important to the casino. Example 1. Consider the game described below. Big win, probability 0.07, small win, blank, lose 0.84. Cost to play, $15, big win pays $120, small win pays $60. What is the expected value of this game? Right. Notice that there's a missing blank here. So the first thing we actually need to do is find that missing blank. How do you find a missing blank? Now, one fact about probability is that if I add up all probabilities, it needs to add up to 100%, or as a decimal, 1. So all three probabilities, if you add them together, it should equal 1. Okay, so what is the missing number so that this adds up to 1? So one way to find out is add up what you have so far. So 0.07 plus 0.84. Okay, and that's 0.91. And then all you need to do is do 1 minus 0.91. And you get 0.09. Okay, once again, add up the probabilities that you have so far, which is 0.07 plus 0.84. You get 0.91, and then just do 1 minus that, and that should give you the missing number. All right, so now we have everything we need to do to find the expected value. Okay, first thing we need to do is write down the profit. So for this game, a big win, you win $120, but you always have to subtract off what you paid to play. So 120 minus the $15 that you paid to play. So 120 minus 15 is 105. So this is a plus 105. Small win is $60, and then also subtract off the cost to play. So 60 minus 15, let me do this on the calculator, plus 45. And then you lose, you get nothing, so you're down what you paid to play. So you're minus 15. All right, and then to find the expected value, probability times profit plus probability times profit plus probability times profit. So the expected value, EV, 0.07 times 105 plus 0.09 times 45 plus 0.84 times negative 15. All right, so on a calculator, 0.07 times 105 plus 0.09 times 45 plus 0.84 times negative 15. Negative 1.2. Okay, if you're playing this game many thousands of times, on average, each time you're playing, you are losing $1.2, so $1.20. Example 2. Consider the following game. You are dealt one card from a standard deck of cards. The game costs $10 to play. If you get a red 10, the game pays $40. If you get a face card, the game pays $25. If you get a spade, the game pays $16. What is the expected value of this game? Now, notice that I didn't give you a table, so you have to make your table. Okay, outcome, probability, and then profit. Okay, so what are all the ways that we can win in this game? You can win if you get a red 10, right? So if you get a red 10, what else? You get a face card, you win. If you get a spade, you also win. And then otherwise you lose. Right, so there's a lose. What's the probability of getting a red 10? So here we're now using what we talked about in the last two lectures, which is finding probability for cards. And here for this one, you're dealt one card, right? So you should end up with just one fraction. Right, so where are my cards? Okay. The bottom is going to be how many cards total? 52. The top, red 10s. How many red 10s are there? Red 10s, I see 2. 10 hearts, 10 diamonds. So two red 10s. Okay, let's actually go through and find all the probabilities. We'll have to enter this in a calculator and get a decimal at some point also. Next one, face. The bottom's going to be 52. How many face cards are there? So face would be Jack, Queen, King in all 4 rows. So Jack, Queen, King times 4. So 3 times 4. There's 12 face cards. 12 out of 52. Spade. Bottom is 52. How many spades are there? Spades is the second row. Okay, how many cards are there? 1 through 10 plus Jack, Queen, King. 13. Now, to find expected value, we actually need these fractions as decimals. Okay, so on my calculator, let me turn off the cards calculator. All right, 2 divided by 52. So 2 divided by 52. Okay, you should get a long decimal. Let's round to 3 decimal places. So round to 3 decimal places. This would be 0.038. Face, 12 divided by 52. 0.231. Spade, that's 13 divided by 52. 0.25. And then I also need a probability for just losing. And that's going to be the missing probability. Okay, so the way we found the missing probability is add up what you have so far. So 0.038 plus 0.231 plus 0.25, which is 0.519, and then do 1 minus that. So 1 minus 0.519. And that should give you the missing probability, which is 0.481. All right, so now let's talk about the profits. If you get a red 10, you win $40. Whoops, let me turn off the calculator right now. If you get a red 10, you win $40, but then keep in mind that you have to subtract off what you paid to play. So $40 minus the $10 to play. So 40 minus 10 is plus 30. So plus 30 for the red 10. Face, you win $25 and then subtract off what you paid to play. So 25 minus the 10, that's plus 15. Spade, the game pays $16, so $16, and then once again minus what you paid to play. So 16 minus the 10, that's 6. That's a plus 6. And then if you lose what you paid. So you paid $10. If you just lose, then you lost the $10. So minus 10. Okay. Now once we have the probabilities, then the profits, expected value, probability times profit, etc. The expected value is going to be 0.038 times 30 plus 0.231 times 15 plus 0.25 times 6 plus 0.481 times negative 10. All right, so I'm going to type that into the calculator. 0.038. Oops. 30 plus 0.231 times 15 plus 0.25 times 6 plus 0.481 times negative 10. 1.295. Consider the following game. You roll 2 20-sided dice. You win if both numbers are bigger than 16. The game costs $3 to play, and a win pays $60. What is the expected value of this game? So once again, we don't have a table of probabilities, so we actually have to find those ourselves. Right. So how do we win this game? There's only one way to win. You win if both numbers are bigger than 15. So both bigger than 16. Otherwise, you lose. Right? So what's the probability that both are bigger than 16? Here we're talking about 2 dice, right? So I should have 2 fractions. And what's the probability that both of them are bigger than 16? So when I roll a 20-sided dice, I could get a 1, 2, 3, 4, all the way up to 20. So first one, I want it to be bigger than 16. Second one, bigger than 16. The bottom, how many numbers could I get total? It's 20. And how many numbers are bigger than 16? Bigger than 16, you don't include 16, so bigger than 16 would be 17, 18, 19, 20. Four. Right. Second one, I also want to be bigger than 16. Now, remember, dice is the only situation where you don't reduce for the second fraction, so the bottom's still going to be 20. Bigger than 16, still going to be 4. Okay, and we have to actually compute this on a calculator. So here's a calculator. So 4 over 20. I'm going to click on the fraction button. 4 over 20. Move the cursor to the right. Times. So either click on the times button, or you can use the star, the symbol that's on your 8, Shift 8. Another fraction, 4 over 20. 0.04 is the final answer. Okay, that's the probability that both of them are bigger than 16. We have to find the probability of losing, which is the missing one. So just take 1 minus 0.04. $0.96. And now let's find a profit. Okay, so if both are bigger than 16, you win $60, okay? But the game costs $3 to play, so you have to subtract that $3 off, which means you're at 57. So profit of 57. If you lose, you just lose the $3 that you paid to play, so you're down 3, negative 3. And then expected value, probability times profit, 0.04 times 57, plus 0.96 times negative 3. Negative 0.6. So this is definitely a game that you don't want to play for long. Let's play it anyway. Okay, so I'm going to roll 2 20-sided dice. So 1, 13, 7. Okay, so you only win if both of them are bigger than 16, so definitely you lost. Example 4. Consider the following game. You are dealt 3 cards from a standard deck of cards. You win if all 3 cards are red. The game costs $3 to play. A win pays out $30. What's the expected value of this game? All right, so same thing. So this game, the only way to win is to get all 3 cards red. So all 3 red. Otherwise, you lose. So now we're talking about cards. All 3 red, so we're talking about 3 cards. I should have 3 fractions. So I went red, red, red. For the first fraction, the bottom, how many cards total? 52. And then how many are red? Red would be bottom 2 rows. Okay, each row has 13. So bottom 2 rows together would be 26. Now, for cards, you do reduce. Okay, so for the next fraction, we only have 51 cards to choose from because we already chose 1 card for the first slot. And then for the third fraction, we're down to 50. Up top, I want a red card, keeping in mind that I already chose 1 red card for the first slot, which means I'm down to 25, and then I'm down to 24. Okay? So on my calculator, fraction button, which is the A over B on the right side, 26 over 52, times another fraction, 25 over 51, another fraction, 24 over 50. And then round to 3 decimal places here, so that's 0.118. And then lose is the missing number, so just do 1 minus 0.118. And that's 0.882. All right, profit. If you do get 3 red, you win $30. But then you also paid, what did we pay? We paid $3 to play. So you have to subtract off the $3 that you paid to play. So 30 minus 3, you're at 27, so plus 27. If you lose, you get nothing, and you just lost the $3 that you paid to play. So you're down 3, negative 3. Expected value is going to be probability times profit, 0.118 times 27 plus 0.882 times a negative 3. Whoops, sorry. Probability times profit plus probability times profit. So 0.18 times 27 plus 0.882 times negative 3. 0.54. So you should play this game as long as possible, many, many thousands of times. So let's actually play this game. Okay, so we're dealing 3 cards, and you win if all 3 are red. Okay, so you lost, but based on expected value here, you should actually keep on playing. You keep playing and wait for the win. Because in the long run, as long as you keep on playing, overall, on average, each time you're playing, you're winning 54 cents. Example 5. Consider the following game. You're dealt 3 cards from a standard deck of cards. You win if you get at least 1 face card. The game costs $6 to play, and a win pays $20. What is the expected value of this game? So outcome, probability, and I think I'm going to need some space here for probability, so because it's at least 1. So let me give myself some room. Right. Now the only way you win is if you get at least 1 face. Otherwise, you lose. Now, remember, the way we calculate at least 1 is 1 minus none. So none face. All right, so it's going to be 1 minus. How many fractions do I need? How many cards are we talking about here? We're dealing 3 cards, so 3 fractions. And remember, these 3 fractions, I want none of them to be face, which means I want them to be no face, no face, no face. So even though I'm looking for at least one face. Because we're talking about complements here, it's no face, no face, no face. All right, so let's find these probabilities. Okay, first fraction, the bottom, total number of cards, 52. And then we're talking about cards, so we are going to reduce. So 52, second fraction, the bottom is going to be 51, and then 50 for the third fraction. First fraction, how many no face? So how many cards are not face? So not face would be A through 10. Okay, that's 10 times the 4 rows. So A through 10 in each row. That's 40 total. And then the next one, I also want to be no face. Because we're talking about cards, you do reduce. So this is going to go down to 39, 38. And now let's type this into a calculator and see what the probability is. So we're going to do 1 minus fraction 40 over 52 times another fraction 39 over 51 times another fraction 38 over 50. 0.553. Now, the missing lose, just do 1 minus 0.553. And that's 0.447. All right, so the at least one face is 0.553. The lose is 0.447. And now let's talk about the profit. If you get at least one face, you win and you get $20, but then you have to subtract off what you paid to play, which was 6. So 20 minus 6 is a plus 14. If you lose the $6 that you paid to play, so you're down 6. And then to find the expected value, probability times profit plus probability times profit. 0.553 times the 14 plus 0.447 times the negative 6. $5.06. So this is definitely a game that you should play as much as possible. Because in the long run, as long as you keep playing, on average, each time you play, you're winning $5.06. So let's actually play this game for fun. But we're only playing it one time. All right, so 3 cards, at least one face. First card. You win already. All right, example 6. Consider the following game. You roll 3 20-sided dice. You win if you get at least one that is multiple of 3. The game costs $5 to play, and a win pays out $11. Okay, so this is another at least one. Okay, so for at least one, I know I need 1 minus a bunch of fractions, so I'm going to give myself some space here. Okay, so the only way to win this game is to get at least one multiple of 3. And then otherwise, you're going to lose. Okay. The way you find at least one multiple of 3 is you're going to do 1 minus the probability that none are multiples of 3. This is going to be 1 minus. How many fractions do I need? Okay, so usually it's either 2 or 3 fractions, depending on how many dice or how many cards you're using. Here we're rolling 3 dice, so 3 fractions. Okay, none of them multiple of 3 means not multiple of 3, not multiple of 3, not multiple of 3. Okay, so I don't know why I said no face there. I should say not face. I went not face, not face, not face. Okay, so we're talking about dice. When you roll a dice, you can get 1, 2, 3 all the way up to 20. Okay, and I want not multiple of 3. So let me actually find a multiple of 3 and then I'll count the other stuff. So multiples of 3 are, counting by 3s, it will be 3. Plus 3 is 6. Plus 3 is 9. Plus 3 is 12. Plus 3 is 15. Plus 3 is 18. Okay. So now back to my calculation. For the bottom, how many numbers total when you roll a dice? It's 20. And when we talk about dice, you don't reduce. So all of the other fractions will also be 20. And then how many are not multiples of 3? Okay, so how many are not circled? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14. Okay. Next fraction, we're talking about dice, so you don't reduce. So 14, 14. All right, let's calculate that. So 1 minus fraction 14 over 20 times fraction 14 over 20 times another fraction 14 over 20. And this is 0.657. And then for lose, it's the missing number. Just do 1 minus 0.657. 0.343. Right, now the profit, if you get at least one multiple of 3, you win, and you actually win $11, but you have to subtract off what you paid to play, so 11 minus the 5 that you paid to play. That's going to be a 11 minus 5 is 6, so that's a plus 6. If you lose, you get nothing, so you lost the $5 that you paid, so you're down 5. And then expected value. 0.657 times 6 plus 0.343 times a negative 5. This is 2.227. Okay, so this is another one that you definitely should play. And let's play. All right, so here's the dice. I'm going to roll it 3 times. You win if you get at least one multiple of 3. Okay, first one. 11, that's not a multiple of 3. 2, not a multiple of 3. 16, not a multiple of 3. Okay, so in this case, you don't win, but based on the calculation here, you should keep on playing until you win. And after that, you should also keep on playing, because overall, if you play this many thousands of times, on average, each time you play, you're winning $2.23. So you definitely should play this game. All right, that's it for this unit. Have a great day. See you later.